Hi class, in this video we continue in chapter 14 by moving into section 14.6, and in this section we're going to talk about something called directional derivatives and the gradient vector. Okay, so in this section we introduce a type of derivative called a directional derivative. What this does is it enables us to find the rate of change of a function of two or more variables in any specific direction. Okay, so let's talk about this. Recall that if z is a function of x and y, then the partial derivatives of we call partial derivative of f with respect to x and partial derivative of f with respect to y are defined as the following limits. Okay, these represent the rate of change of z in the x and y direction. So that is in the direction of the unit vectors I and j. Okay, that's what this one does for I and this one does for j. So if we take the limit as h goes to 0, we obtain the rate of change of z with respect to distance. All right, in the direction of some unit vector u, all right, which is called the directional derivative of f in the direction of u. So here's just the formal definition. The directional derivative of f at some specific point x0, y0 is the direction of a unit vector u with components a and b, and we denote it as the following. The directional derivative in the direction of u of the function f at some specific point x0, y0 is given by this limit. And notice how both the x and the y have the HA and HB here. So h plus a and h plus b for the y. Okay, and this directional derivative is defined if the limit exists. So if we compute the directional derivative of a function defined by this formula, we generally use this following theorem. If f is a differentiable function of x and y, and f has a directional derivative in the direction of any unit vector with components a, b, then we have the following. The directional derivative of the function f of xy in the direction of u is given by the partial derivative of f with respect to x times a plus the partial derivative of y times b. So it's pretty straightforward formula actually here. All right, so let's just do a quick example here. So let's just find the directional derivative of the following, okay, where we have a function of three variables. So if you notice and go back, I've defined everything in two variables, but it's easily expandable to three variables, piece of cake. So where our function x, y, and z is x squared z plus y cubed z squared minus x, y, z in the direction of this vector, all right, with components -1, 0, 3. Okay, this formula only works, or we only use it when you have a unit vector. Okay, so that's important. Remember, you got to check to make sure that it's a unit vector. All right, so first we're going to check to see if it's a unit vector in the direction that we want. So we can do this by checking its magnitude. So if you check the magnitude of this vector, it's not equal to 1. It's equal to the square root of 10. So it's not a unit vector, but recall that we can convert any vector into a unit vector that points in the same direction, just dividing that vector by its magnitude. So let's do that. So now we're going to take this vector, divide it by its magnitude, and we get the following vector here. Okay, so this is a unit vector that we need that points in the same direction as this vector here. So then the directional derivative is just the following. And we're just going to follow this formula. Okay, the only difference is this problem is in three variables, so we're going to need plus the partial derivative of f with respect to z times c. All right, so we're going to take the a component, multiply by the partial derivative with respect to x. You take the derivative of this with respect to x, you get the following. Plus the second component times the partial derivative with respect to y. So you take the partial derivative with respect to y, you get this. Plus the third component times the partial derivative with respect to z, you get the following. And if you were to just clean this up a little bit, you'll see that the directional derivative in the direction of this vector, all right, is given by this function right here. So that's it. So it's really just, as you can see, a lot of this stuff is just following the formula. All right, so again, if the kind of like a corollary of this, if the unit vector u makes an angle theta to the positive x-axis, then we can write u as cosine of theta, comma sine of theta, and then we can just change the formula a little bit to be the directional derivative of f of x, y in the direction of u is the partial derivative with respect to x times cosine of theta plus the partial derivative of y times sine of theta. So this is just another way to do this problem. All right, let's talk now about the gradient vector. So notice that in our theorem 3 in this lecture, that the directional derivative of a differentiable function can be written as the dot product of two vectors. So you can write it as the vector with the partial derivative of x, comma, the partial derivative of y, times the unit vector. This first vector right here in the dot product occurs not only in computing directional derivatives, but there's many other contexts as well. So we give it a special name, and it's called the gradient of f, and it's got a special notation. So grad f, or the gradient of f, all right, this, which is also read as del f, okay? So I will call it sometimes just the gradient of f here, or you might hear me call it del f as we go through this, and that's just this part right here. Okay, if f is a function of two, so here's the formal definition. If f is a function of two variables x and y, then the gradient of f is the vector function del f defined by just the following. It's just the partial derivatives corresponding to their variables, and you can also write it as the partial derivative of f times partial derivative of f with respect to x times I, plus partial derivative of f with respect to y times j, as another way of showing this vector. All right, let's just do an example real quick. All right, so if let's take this one. Let's take f of xy, which is sine of x plus e to the xy, and find its gradient vector. And then let's just evaluate the gradient vector at the point 0, 1. Okay, so del f of x is the partial derivative of x, comma, the partial derivative of y. Well, the partial derivative of x here ends up just being cosine of x plus y e to the xy, comma. The partial derivative of y here ends up just being x e to the xy here. And so we could say the gradient at point 0, 1 is the vector 2, 0. All right, so just following directly the formula. All right, so with the notation for the gradient vector, we can rewrite equation 7 in this lecture for the directional derivative of a differentiable function as the following. So the directional derivative of u is equal to the gradient function dot product with the unit vector pointing in the direction we want. So this expresses the directional derivative in the direction of a unit vector u as a scalar projection of the gradient vector onto u. This is what this formula does. All right, you can also expand this into 3 variables. You see the formula works exactly the way you would think it would be if you have a function of 3 variables. So I just expanding on with the k component here. All right, then just as with functions of 2 variables, you can also have the following formula here for the directional derivative if you have a function of 3 variables. All right, let's work an example, okay? If you have a function of 3 variables, x, y, and z, and your function is x sine of yz, let's find the gradient of f, and b, find the directional derivative of f at this point, 1, 3, 0. So this is our point in the direction of this vector, I plus 2j minus k. All right, so first off, let's find the gradient of f. That's incredibly easy. So del f here is the partial derivative with respect to x, comma, the partial derivative with respect to y, comma, the partial derivative with respect to z. So just going through the partial derivative of x of this function with respect to x is just sine of yz. Here the partial derivative with respect to y ends up being just xz cosine of yz. And the partial derivative with respect to z just ends up being xy cosine of yz. All right, next thing we have to do, we have to change this to a unit vector. So changing this to a unit vector because we want it pointing in that direction, okay? We're going to take this and put it in terms of a unit vector, okay? So we're going to take that and divide it by the square root of 6 to change it to a unit vector. All right, plugging this point into the gradient vector also gives us this vector right here. So therefore, equation 14, all right, the directional derivative of our function at the point 1, 3, 0, all right, in the direction of this vector ends up just being the following. And you can work out the dot product yourself to see this here. All right, class, I hope this helps. I know there was a lot of formulas in here, but just follow the formulas and you'll be okay.